Good morning. Thank you for coming back. We'll see what happens next week. All right. This week, the topic is methods for discovering exoplanets. If you remember what the course is about, we are interested in the discovery of planets around other stars because we are interested in why we're interested in those planets. We're interested in those planets because of the impact of discovering those planets. In particular, what we're going to talk about at the end of this course, the last few weeks, will be the impact of thinking about those planets for religion, for exotheology. But first I have to convince you that astronomers know how to discover planets around other stars, that we actually know those planets are out there. So last week we talked about primarily history, the ideas that people used to have about life in the universe, all of which was based on absolutely nothing. All right. So now we're going to try to change that and try to understand that astronomers actually do know something about planets around other stars, and this week is all about technique, how we know something about planets around other stars. The first thing I want to do is get you thinking like me, thinking about those planets around other stars. So I have a simulator for you to look at, and I think the internet is working. So I have to make an adjustment here. We have two stars in orbit around each other. I'm going to have you look at the stars as if we're above the orbital system. Most of us, when we think about planets orbiting stars, actually think about planets orbiting stars. But you can't think that way. You have to recognize that objects orbit each other. And when we have two stars that are equal in mass to each other, one star doesn't orbit the other star. The two stars orbit each other. They orbit a point in between the two of them, which is known as the center of mass of the system. And that point is designated by that little cross sign in between the two stars. If I change the masses of the two stars, so what I'm going to do here is I'm going to adjust the mass of one star and make it large. And I'm going to adjust the other star and make it very small. It appears that one object is orbiting the other, and I'm also going to make the orbit very circular. And I'm going to make one object really tiny looking. So now it looks more like a planet orbiting a star. And it looks like one object is actually moving around the other object. But it's not. They are orbiting the center of mass of the system. And again, I'm going to adjust it a little bit so that we know that both objects are moving, and I'm going to make the radius of that object in the middle a little bit smaller so you can see it actually does move. Both objects always move. The big object, the more massive object, may only move a little bit, but it moves. And now I'm going to tilt the system a little bit so that we're looking at it closer to edge on. In some systems, we may be looking at the system so that one object is coming toward us and the other object is coming away from us. And the object in the middle, the big guy, the star, may just come toward us a little bit and away from us a little bit, but it's moving. In a star-star system, both objects move a lot. In a star-planet system, the star doesn't move much. The planet moves a lot. So we talk about the Earth orbiting the Sun. But the Earth and the Sun are orbiting the center of mass of the Earth-Sun system. that center of the mass of the Earth-Sun system is deep inside the Sun. So the Sun doesn't move much, but the Sun moves. For most of the history of astronomy, what astronomers were trying to do for detecting planets was actually detect the motion of the star by actually looking and seeing that star move, the physical movement of that star in the sky. That's one way of trying to detect the presence of the planet. If you see the star actually move, it's moving because the planet's tugging on it. So you can infer the existence of the planet because the star is wobbling. A second way of inferring the existence of the planet is not by seeing the star itself move, but by measuring the velocity of the star, which is also a manifestation of the star's motion. Yes?
Is the center of mass for the Sun and Mars different or the same as it is for Earth?
Is the center of mass for the Sun and Mars different or the same as the center of mass for the Earth and Mars? It's different. For each planet-star pairing, it's a little bit different. All right. So there are different ways of detecting the presence of a planet. We're going to talk about 3 of those ways today. But I need you to be thinking about this picture. You need to have this in your mind to remember planets don't orbit stars. Planets and stars orbit the center of mass of the system. The star is always moving. It just doesn't move a lot. The star moves, the planet moves a lot. Yes? How do you find the center of mass? Is it not always the star? The center of mass will always be closest to the big object. And the bigger the star is compared to the planet, the closer the center of mass will be to the center of the star. So if I have a big star and a little planet, the center of mass will be deep inside the star. If I have a big planet and a little star, the center of mass could be outside the star, closer to the planet. And the star might move a lot. How do you find it? By looking. How do you look? With a telescope. We're going to talk about that. Yes, sir.
Is it true then that while the star moves in a circle, if there's one planet, if there are 9 planets, that circle is defined by the attraction of all 9 planets?
If we're just talking about one planet and one star, then we just have to worry about this nice simple picture. But as you suggest, if there are 9 planets and one star, then effectively there are 9 different centers of mass, and that star is going to kind of wiggle all over the place because all 9 planets are pulling on it at once, and the star is going to be tugged on in 9 different ways, and it's not going to move in a simple way. So the star is going to have a complicated motion because all 9 planets are pulling on it at the same time, sort of like if you've got 6 kids, they're all pulling you in 6 different directions, and life is complicated. So for a planetary system with multiple planets, life is complicated for the star and is being pulled all over the place.
Is it consistent, though, even if it's complicated with all these different planets pulling on the star?
Is it consistent in the sense that the laws of physics determine what's going on? Yes. If you knew the masses of the 6 planets and the location of the 6 planets and the orbits of the 6 planets, you'd know exactly what that star is doing. Again, if you knew the orbits of the planets and the locations and the masses of the planets, yes, from year to year, there's a pattern that the star would follow that you could predict.
Could you give us a URL of this, an address, so we can enjoy this in the privacy of our own homes?
Yes. It's right there. Or you can just Google astronomy education at the University of Nebraska-Lincoln, and you'll find that address. I'll leave that up for a moment. And I could have that emailed out to you if you want. All right? Does the universe have a center of mass? If the universe is finite in size, then in principle, yes, it could have a center of mass, but the universe may be infinite in size, in which case we couldn't find the center of mass, no. So I can't give you a yes or no to that answer. It might. If there are 9 planets like our solar system, Pluto, yes. Right. And they're all pulling the sun or the star in different directions, how long does it take the system to go through the cycle? The cycle is constantly changing because Pluto takes 248 years to orbit, and Saturn takes 60 years, and Jupiter 12 years, and the Earth 1 year. And they're all at different places at different times, always. So there's no 1 year or 1 decade or 1 century in which the positions of the planets exactly replicate what they were 100 or 1,000 years ago. So every day is different. All right.
What about the changes of the orbits of the planets as the planets themselves move the sun around? Does it change the orbits of the planets?
What about the changes of the planets do tug on the sun, and because the planets tug on the sun, that affects the position of the sun, which then affects the interactions with the planets, which in effect the interaction with the sun. So it's a continually changing process. Because the sun is so big compared to the planets, effectively there's a great deal of stability to a planetary system because the star is so dominant. In other systems where you might have multiple stars or planets which are much bigger compared to their stars than our planets are, the situation could be a bit different. All right, I'm going to move to my next slide. All right, the first method I want to talk about for detecting planets is known as astrometry, which is simply astronomers measuring the positions and the movements of stars in the sky. And to get started understanding this, you have to do what all students in intro astronomy classes do. And that is they put their finger on their nose. So go ahead. Put your finger in front of your nose, and you have to blink your eyes. First set one eye, and then the other eye. And watch your finger. What does your finger do? It moves. No, your finger didn't move. Your finger appeared to move, because you looked at it from a different viewing position, right? But your finger didn't move. Now, put your finger at arm's length and blink your eye. Did your finger appear to move as much? All right. The further away something is from you, the less it appears to move when you view it from a different viewing position. So your eyes enable you to measure distance. All right? The further away something is, the less it appears to move. You judge distance that way. That's how you park a car. If your some of you, if your insurance is paid up, your car insurance, you can try to parallel park a car with one eye shut. Okay? 2 eyes work better. All right. So you measure distances by measuring the location of objects from 2 different angles. Well, astronomers do this by measuring the locations of stars from 2 different angles. So when the Earth is on one side of the sun, which in this cartoon here is marked January 1st, and on the other side of the sun, July 1st, when the Earth is on one side of the sun versus the other side of the sun, if we find a relatively nearby star, it will appear to move it will appear to be over here to the left on July 1st, and then over here to the right on January 1st, and that nearby star will appear to move back and forth across 6 months. The star is not moving, right? Your viewing position is moving. The Earth is moving. It's like your left eye and your right eye. This is what astronomers call parallax. And what we're measuring is the angle that the star appears to move. And that's what you're doing with your eyes. When your finger's right in front of your nose, your finger seems to move a lot. You're measuring an angle that your finger appears to move. When your finger's far away, your finger doesn't appear to move as much. You're measuring an angle. So the job for astronomers for this parallax is to measure the angles by which stars appear to move. And the first person who first was able to measure the parallax angle for a star was Friedrich Bessel. And he gets a stamp. All right? I think he's our only stamp today. He is an important astronomer, one of the most important astronomers of the 19th century, because he measured the first parallax angle for a star, which meant he measured the distance to a star. The star he measured was 61 Cygni. 61 Cygni is in the constellation Cygnus. It's not a very prominent star, but I thought I had another slide here. It's missing. All right. It came to our attention, it'll show up eventually maybe, came to our attention in the early 19th century because it moves a lot. Okay? And it's a star he began to study. Before we get to that, we need to talk about angles to understand how hard it is for astronomers to measure angles. So now you have to go back to elementary school, way back. You know there are 360 degrees in a circle. In 1 degree, there are 60 minutes of arc. So you chop up 1 degree into 60 pieces, you get 1 minute of arc. Then you take 1 minute of arc. You chop that up into 60 pieces, you get 1 second of arc. Just like taking an hour and chopping it up into 60 minutes of time and chopping it up into a minute into 60 seconds of time. Well, we chop up degrees into minutes, and we chop up the minutes into seconds. There are 3,600 seconds of arc in 1 degree. 1 degree is a pretty small angle. 1 second of arc is a pretty small angle. Astronomers measure distances in the sky using this idea of seconds of arc and minutes of arc. So when we look out in the sky, we think about measuring the angular distance between 2 objects, between 2 stars. And we can measure that distance in degrees of arc or minutes of arc or seconds of arc. A second of arc is a pretty tiny angle. The full moon is about half a degree across. About 30 minutes of arc across, about 1,800 seconds of arc across. The full moon changes in size depending on where the moon is in its orbit. The moon is not in a circular orbit. The moon's orbit is elliptical. Sometimes the moon is further from the Earth. Sometimes the moon is closer to the Earth. When the moon is at what's called perigee, when it's closest to the Earth, it appears bigger. When it's at apogee, when it's furthest from the Earth, it appears smaller. So you can see the apparent change in angular size of the moon. The moon's not changing in physical size, it just appears bigger or smaller because it's closer or further from the Earth. So what did Bessel try to do? Well, here's the slide I was looking for. In 1804, an Italian astronomer, Giuseppe Piazzi, identified or recognized that the star 61 Cygni was unusual. It moved. It had what astronomers call proper motion. Proper motion means it just moves. Most of the stars are known as fixed stars. They just don't seem to move. You probably learned when you were pretty young that there was a constellation out there called the Big Dipper. Right? And the stars in the Big Dipper are pretty much in the same place. You can recognize the Big Dipper now. You can teach your grandchildren about the Big Dipper. They can teach their grandchildren about the Big Dipper. The stars in the Big Dipper stay in the same place. But there are some stars that appear to move just a little bit, or just a little bit more than other stars. And Piazzi recognized that 61 Cygni was one of those fast-moving stars. And he dubbed it the flying star. And that brought it to people's attention because that meant it probably was a little bit closer than other stars. And that's why it appeared to move faster than other stars. And if it was closer than other stars, that meant it would be one of the stars that would be easier to measure the parallax of than for other stars. And for those people like Bessel who hoped to become the first person to measure the parallax of a star, 61 Cygni was a good candidate. So he studied 61 Cygni, and in 1838 he managed to measure the parallax of 61 Cygni, the first star for which we actually knew the distance. The parallax of 61 Cygni, 0.3 seconds of arc. Now the modern value is 0.286 seconds of arc, so he didn't get it quite right. He did a pretty good job. 0.3, 1/3 of a second of arc. Not 1/3 of a degree. Not 1/3 of a minute. 1/3 of a second of arc. All right? So imagine the full moon. 1,800 seconds of arc across. This is 1/3 of 1/1800th of the full moon. It's a very, very tiny angle. 61 Cygni, as it turns out, is a binary star system. So there are two stars in that system. One of them appears to orbit the other. They orbit each other. But one of them appears to orbit the other in an orbit that takes it about 678 years. So you can sort of see the general orbit of the 68 Cygni system. It's at about 11 light years from the Earth. 61 Cygni is a well-studied system. All right. Now let's talk about what astronomers call seeing. Good seeing and bad seeing. See Jupiter on the left in bad seeing, and Jupiter on the right in good seeing. You can just call it blurry vision and good vision. On the top, you see 5 different images of a single star. On the left is a really good image of a single star. On the right is a really bad image. On the right, you see what are called speckles. On the left, you see what's called an airy diffraction pattern. Telescopes require that the light go through a tube and hit some mirrors, and you end up getting this pattern in which you have a central disk with these rings around it. Okay? Stars don't have those rings around them. That's the result of the light going through the optical system of the telescope. It's the diffraction pattern. You don't see that diffraction pattern unless the seeing is excellent. If you go out tonight in Nashville and look at the stars, assuming it's not cloudy, the stars will twinkle. Astronomers don't like twinkling stars. Twinkling stars mean you see these speckles. It means the light is bopping around, moving all over the place, because the air is turbulent, because there's water vapor in the air, because the air is windy. Astronomers like incredibly cold winter nights, when there's not much water vapor in the sky, when the air is very still. My students in lab do not like cold winter nights. Oh well. Okay. But the seeing is much better on cold winter nights. Astronomers like high mountains, when you can get above most of the atmosphere and most of the water vapor in the atmosphere. Even better, astronomers like to put their telescopes in space, when you get above all of the atmosphere, because the atmosphere is a huge problem for astronomers, because it blurs the images. The image on the right with all those speckles, that's a typical seeing blob. Okay. Highly technical term. Okay. We would call it a seeing disk. In here we'll call it a seeing blob. That blob, that twinkling blob, is typically 5 or 6 or 7 or 8 seconds of arc across. Seconds of arc. That's the typical size of a star. If you take a photograph with a camera of the sky, those blobs of stars are typically 5, 6, 7, 8 seconds of arc across. So how are you going to measure the parallax of a star that's 1/3 of a second of arc across? In excellent seeing on Mauna Kea in Hawaii at 14,000 feet, when the weather is fabulous, you get seeing of a couple of tenths of an arc second. Well, Friedrich Bessel did not observe from Mauna Kea at 14,000 feet. He was in Central Europe, and he was able to make that measurement of 1/3 of a second of arc. It was fabulous work, incredible work. Measuring the parallax of stars is incredibly hard to do because the stars are far away. All right. Measuring these angles is small. If measuring the parallax of stars is hard, measuring the motions of the stars, because they're being tugged on by their planets, is going to be even harder. All right? The motions of the planets, because the Earth is tugging on the sun, the sun doesn't move much. Or Jupiter is tugging on the sun doesn't move much. Does it move a second of arc? Fat chance. Does it move a tenth of an arc, second of arc? Fat chance. It doesn't move a degree. It doesn't move a minute of arc. It doesn't move a second of arc. It doesn't move a tenth of a second of arc. The angles by which the stars move because the planets are tugging on them are incredibly small angles. Almost immeasurably small angles. In fact, from the ground, they are immeasurably small angles. However, in the early and middle part of the 20th century, some astronomers did not think they were immeasurably small angles, and they thought they could measure those motions. So they measured those motions. The first person who thought he succeeded was an astronomer named Strand working at Swarthmore College. And in 1943, he claimed that he had discovered a planet in the 61 Cygni system. Why 61 Cygni? It's a close star. We know it's a close star because Bessel measured the parallax. If you're going to discover a planet, the best candidate stars would be the closest stars. And he knew 61 Cygni was close. So he studied 61 Cygni. And 61 Cygni is in this orbit. So what was he doing? He's watching the orbit of 61 Cygni, and he's trying to see the star wobble. Instead of following the exact orbit it's supposed to follow, it wobbled a little bit because it was being tugged on by a planet, right? How much did it wobble? Well, look at the numbers here. Instead of following the path it's supposed to be following, the straight line here, it's wobbling. It's wobbling. And how much is it wobbling? Well, if you can read the numbers on this axis, 0.01 seconds of arc, plus 0.01, 0.02 seconds of arc. It's wobbling up and down by 1/100th of a second of arc. 1/100th of a second of arc. He thought he was measuring the motions at the level of 100th of a second of arc. He was fooling himself. He probably could have done some calculations to figure out whether or not that was possible. Whether the planet tugging on the star could have tugged it even that hard. And he would have discovered that physically that was impossible. But I don't think he did the math. But he thought he had discovered a planet. And he thought the planet was 16 times the mass of Jupiter. Jupiter is 318 times more massive than the Earth. So this planet would be, you do the math, a whole lot more massive than the Earth, right? A very, very big planet. These days, we would not even consider that object a planet. We would consider that object a brown dwarf. But he thought he had discovered a planet in a 5-year orbit, a 4.9-year orbit around 61 Cygni, 1943. In the same year, somebody else did the same thing. The star 70 Ophiuchus, this star right here, this incredibly prominent star right here, 70, in the constellation Ophiuchus, became the subject of study. It also is a binary star system. 70 Ophiuchi has an 87.7-year orbit. It's also a fairly close star. And two astronomers at the University of Virginia, Royal and Holmberg, announced that they had discovered a planet 10 times more massive than Jupiter, 3,000 times more massive than the Earth, in a 17-year orbit around one of the stars in the 70 Ophiuchus system. They didn't know which star. And again, you can look, the star should have been following this straight line path in its orbit, but it was deviating. This top plot is for what's called declination, the bottom right ascension. That's like latitude and longitude on the Earth. Astronomers just use their own language. And again, you can see the numbers here, 0.3 seconds of arc, minus 0.3 seconds of arc. So this star is wobbling up and down by about 1/10 of a second of arc, which is a whole lot more than 100th of a second of arc, but it's a small number. So is it really wobbling, or is that noise? He thought it was really wobbling. What happened? Well, both of those planets disappeared. Okay? In 1952, 9 years later, Strand, the astronomer who had discovered the planet, the first planet, announced that the 70th planet discovered by the folks at Virginia didn't exist. He had debunked that one. Okay. So the 70th planet was gone for good at that point. There was one other report made in 1978 in which some other folks reported that the data for 70th indicate the absence of any evidence for this planet. It doesn't exist. It never existed. The original discoverers desperately wanted to find a planet. They saw a planet where there was no planet because they wanted to find it. What about the 61 Cygni planet? Well, in 1967, Strand himself revised his data. He announced that his planet wasn't quite as big as he thought. It was only 8 times the mass of Jupiter, and the period was 4.8 years, not 4.9 years. That's the last we heard about that planet until 1978, when some other folks announced that the result was spurious. No one else has been able to find this planet. In 1995, there was a definitive announcement that there is no planet in this system with an orbit of less than 15 years. And modern data confirm there's no planet there. There's no way they could have seen a planet there. Those measurements, those angles are much too small. All they were looking at was noise. They made a mistake, which gave astronomers and astronomy a bad reputation for seeing things that weren't quite there. Fortunately, science is a self-correcting enterprise. If we make mistakes, other people will point them out. Nicely, hopefully. All right, a little closer to home. E.E. Barnard was a youngster who grew up in Nashville. He learned photography downtown and was one of the folks who invented astrophotography by applying his skills to the sky. Bishop Holland McTeer offered E.E. Barnard a position as Vanderbilt's first astronomer. And E.E. Barnard then lived in this little house on campus from 1883 until 1887. And E.E. Barnard is important more for the work he did after he left Vanderbilt than for the work he did here. He took a job at Lick Observatory after leaving Vanderbilt. And while at Lick Observatory, he discovered that that little star right there, an incredibly prominent little star there, which is now known as Barnard's star, is the fastest moving star in the sky. It goes zip, zip, zip. So whereas all these other stars are just kind of sitting still, it moves relative to the other stars. It moves about 10 seconds of arc per year through the other stars. And he discovered that in 1916. So that star is known as Barnard's star. And we get to associate ourselves with E.E. Barnard, so that's kind of cool.
So does it move back and forth? Or does
No.
it keep going?
It just keeps going.
Could it be coming here?
It's not coming our way now. No. Okay. Yes, Barnard Hall was named after him. Any Barnard stuff on campus is named for E.E. Barnard.
Why would it not have a center of gravity?
It's orbiting the center of the Milky Way galaxy. It's not in, as far as I know, in a binary star system, so it's not orbiting another star. All the stars in the galaxy are moving. Most of the stars are far enough away that we don't notice their motions. Barnard's star is relatively close, and it just happens to be moving. So we notice its motion. So Barnard's star came to the attention of another astronomer at Swarthmore College, Peter Van de Kamp, who studied Barnard's star and discovered that Barnard's star had a planet. Sort of. Okay. And here's his evidence for the presence of a planet around Barnard's star. Again, Barnard's star should have been going in a straight line, but it was wiggling. Here, this is the right ascension, which is like, again, the longitude, and here's the declination, which is like the latitude, the other way around, latitude. The right ascension, it's kind of wiggling, going up and down, and the declination's kind of going up and down just a little bit. And the measurements on there are in microns on his photographic plate rather than seconds of arc, so I can't tell you exactly how many seconds of arc or hundredths of seconds of arc it is. But he thought it was moving, and you can see the dates on there, 1940, 1945, 1950, 1955. So Barnard's star is wiggling. And if it's wiggling, it must be because it's orbiting something, or something else is orbiting it. And he inferred the presence of a planet. So here's what we know about that planet. In 1963, that planet had 1.5 times the mass of Jupiter, and it was in a 24-year orbit, according to Van de Kamp. In 1969, with 6 more years of data, he had revised his calculation, and he claimed it was a 1.7 Jupiter mass planet in a 26-year orbit. Now, that's okay. You get better data. You revise it a little bit. In the same year, in 1969, he revised it again. He said, there are actually 2 planets there. The motion's a little bit more complicated. One of the planets is just a little bit more massive than Jupiter, 10% more massive than Jupiter in that 26-year orbit. But the second planet's a little smaller than Jupiter, 80% the mass of Jupiter in a 12-year orbit. This is really cool. This is a planetary system with 2 planets. In 1973, 2 different groups of astronomers said, there's nothing there. The team of George Gatewood, who was at the University of Pittsburgh, and Heinrich Eichhorn, who was at the University of South Florida, using their own data, said, Barnard's star goes in a straight line. There's no wobble, nothing there. Okay? And John Hershey, who embarrassingly, I think, was also at Swarthmore College, and used the same data, the same photographic plates as Van de Kamp, said, there's no planet there. I find no planet. Van de Kamp, however, persevered. He said in 1975, there's only 1 planet, but it's smaller. It's only 40% the mass of Jupiter in a 26-year orbit, and by this point, nobody's paying any attention. It's embarrassing. Okay? In 1982, he revised it again. He said, there are 2 planets, 0.7 Jupiter masses in a 20-year orbit and 0.4 Jupiter masses in a 12-year orbit. At that point, the planets pretty much went away. Van de Kamp didn't do any more work on it. In 2013, an astronomer at UC Berkeley, John Choi, reported with some new data that previous claims of planets around the star by Van de Kamp are strongly refuted. Measuring planets from the ground using the technique of astrometry don't work. The angles are too small. They can't be measured. We can't see these tiny little angles. However, the European Space Agency in December of 2013 launched a telescope specifically designed to be capable of doing this. It's called the Gaia mission. And Gaia is designed to measure the positions of more than 1 billion stars in the Milky Way galaxy, down to an accuracy of 24 micro arc seconds, 24 millionths of a second of arc. This is being done from space, and the technique works, and they will succeed. And their first conferences announcing results will be this summer. And you will start seeing results from the Gaia mission. And it's going to be spectacular. As far as planet detection, this is from the Gaia team's website. For stars within a distance of approximately 150 light years from the Sun, Gaia is expected to find every Jupiter-sized planet with an orbital period of 1.5 to 9 years. It will do this by watching out for tiny wobbles in the star's position. This behavior is caused when a star is tugged by the gravitational pull of a planet in orbit around it. In our own solar system, Jupiter, and to a lesser extent all the other planets, do this to the Sun, making it wobble. Estimates suggest that Gaia will detect between 10,000 and 50,000 planets beyond our solar system with this astrometry technique. We can't do it from the ground, but Gaia will do it from space. This is a plot which looks like a scatter diagram, right? But it's a plot. The horizontal axis here is period. It's a logarithmic plot. 1 year, 10 years, 100 years, 1/10 of a year. The vertical axis is the motion of a star due to the tug of a planet. And each dot is a known planet. And we haven't talked about the planets that have already been discovered through other techniques. But astronomers now know of about 2,000 planets around other stars. We'll talk about that next week. And for all of those stars, the Gaia team has said, if we studied those stars, how much motion would the stars have because of the planets that we already know are there? So for a planet in a 1-year orbit, that is this planet, whatever it is, it would cause its star to move, about 20 micro arc seconds. You can't detect that from the ground. And even Gaia won't be able to detect that. But above about 20 micro arc seconds, above this line here, all of these planets could be detected by Gaia. We know those planets exist. Gaia could detect all of these, so Gaia will detect all of these and others. The interesting one here is this guy up here, the big blob all the way at the top. Because that guy has been detected from the ground. Now, that guy up there, known as DE0823-49b, the quiz will be later. That's up there at 10 to the 4th at the top of that diagram. 10 to the 4th micro arc seconds, which would be 1/100th of a second of arc. That's a very tiny angle. And it's at 1 year. That's this object. It's an object with 28 Jupiter masses. It's not actually a planet. It's a brown dwarf, which is intermediate between planets and stars. But it is probably the first successful detection of an object which is smaller than a star using this technique of astrometry from the ground. It's, again, not quite a planet, and you can see its slight movement at the bottom. What you're seeing in this inset here, the object, the star, should be following this nice path here, but it wobbles a little bit off the path. And it's this slight wobble off the path that would seem to be the indication that there's a planet tugging it, making it move slightly off the path that it should be on. And that slight wobble off its path is due to this 28 Jupiter mass object, which is this DE 0823-49b. So that object is, I think, the only definitive detection of a not quite a star object, but also not quite a planet object from the ground, using astrometry. Astrometry has been a failed technique for detecting planets from the ground. But astrometry is about to explode as a successful technique for detecting planets from space. So keep your eyes peeled, because those announcements are going to come starting, I think, this summer, but certainly within the next year from the Gaia mission. Next technique, radial velocity. You're more familiar with this. This technique has worked from the ground. The radial velocity technique involves measuring the actual motions of the stars. So in this technique, we're not looking to see the actual star move. We're measuring the velocity of the star, toward or away from us. Toward means a blue shift, away means a red shift. And you are a little bit more familiar with this terminology called the Doppler effect. In the early, mid-19th century, the Austrian physicist Christian Doppler said that for sound, the frequency or the wavelength, the sound, the pitch of a sound wave will change if the source of the sound is moving toward or away from us. And a few years later, the French physicist Louis Fizeau said that's going to happen to light too, because light is also a wave phenomenon. And if the source of the light is moving toward you, or the source of the light is moving away from you, the light effectively will change color because the source of the light is moving toward or away from you. So I'm hoping this will work. I've plugged in the sound. We'll see what happens here. No, I don't want to configure this. All right. That's not supposed to happen. All right. So that may not work for us. I had some, and now what happened? We're supposed to be, these are supposed to be simulators of Doppler shift for sounds, but it doesn't look like they're going to work because of this room. All right. So you folks have probably all heard trains and fire engines and ambulances, and you know that when the train whistle blows its toot and the train passes you, the pitch of the train whistle changes pitch as it passes you, or the fire engine sound changes pitch. That's what these were going to be a demonstration of. So there's a question over here. Yes, ma'am. What's the difference between the Hubble and Gaia? Hubble is a telescope. The Hubble Space Telescope has several different measuring devices that are designed. Some of the devices are designed to take pictures. Some are designed to get what are called spectra of different objects. Gaia is specifically designed to measure to do astrometry, to measure the changing positions of objects. Whereas Hubble is not specifically designed to do that. Hubble is designed to make other kinds of measurements of objects. Okay? So they have different astrophysical goals in what the kinds of measurements they're trying to make. Yes? What is the closest star? How long would it take to get to the closest star? The closest star is a couple light years away. And it would take us, at the speeds of the best rockets we have, a few 100,000 years to get there. So we're not going anywhere soon. Okay? I have my students do that calculation on the first day of class. It's a good exercise to either convince them to become engineers and build much, much faster rockets, or to become astronomers and build really good telescopes, because the best way to study the stars is to stay here and study them, because we're not going anywhere soon. The universe is way too big. All right. So no experiments with the Doppler shift, but let's keep talking about the Doppler shift. If you are looking at the source of light or the source of sound, and you are moving away from the source, so the source is here, and you're moving away from the source, and there's an observer over here looking at the source of the light, and the source is moving away, then the yellow light would look reddish rather than yellow. If the source of the light is moving toward the observer, the light would look bluer rather than redder. So we call that blue shifted or red shifted. That's the terminology. And we use that language even if it's sound. Okay. You're also familiar with this with highway patrol officers using their radar guns. With radar, it's sound. With the radar guns, they are bouncing a radar signal off your car. The car is coming toward the officer. The radar signal bounces off the car. They measure the red shift or the blue shift of the radar signal. And they use that to measure how fast your car is going. We use that with weather weather Doppler measuring devices that send out radio signals that bounce off the clouds and measure how fast the clouds are moving, and that can then measure the circulation of clouds. You're very familiar with Doppler shift. What astronomers do, we don't have to send out signals. We can't send out the signals. But the stars are pretty good at sending us the signals. They just send us the light, and we measure the light that the stars send us. Now, stars send us the light. We put the light through a prism. When the light goes through a prism, it's broken up into the different colors of the rainbow that we call a spectrum. And you guys know all about this, and you get all the colors of the rainbow. But for stars, you don't get a nice, clean spectrum. You get something that's illustrated down here at the bottom. You get a spectrum with lots of lines in it. And all of these dark lines, known as spectral lines, tell astronomers about what's going on in the atmosphere of a star. And in here, we don't have to worry about exactly what's going on in the atmosphere of the star. We just need to know those lines are there. And different stars have different lines. Astronomers then classify stars. O, B, F, G, K, M are different classifications used for stars. O stars are hot stars. M stars are cool stars. The sun is a G star. And all these lines tell us about the contents of a star's atmosphere, and the temperature of a star's atmosphere, and the density of a star's atmosphere. They tell us if there's hydrogen, or helium, or magnesium, or calcium, or you pick it. We can measure what's there and how much is there. For our purposes today, the important thing is those lines are there. And if the star is not moving, those lines just sit still. But if the star is moving, those lines move back and forth. So here we have a star which is moving because there's a planet. And the star and the planet orbit the center of mass of the star-planet system. So the planet's moving in a big orbit and the star is moving in a little orbit, but the star moves a bit. So the star is coming toward the Earth, and then the star is going away from the Earth. And when the star is moving toward the Earth, the light from the star is blue shifted. And when the star is moving away from the Earth, the light from the star is red shifted. And up here in the top left, you have a top panel where you see the spectrum from a star with the lines in it. And it's got those dark lines which are labeled as unshifted. And when the star is coming toward us, those lines are red-shifted. So all those lines are shifted a little bit to the right, toward the red. And when the star is coming toward us, all those lines are shifted a little bit to the left, toward the blue. And if we watch the star over time, we see all the lines in the spectrum of the star moving back and forth and back and forth. And the amount of the redshift and the blue shift and the time it takes for the lines to move back and forth tell us about the orbit of the star. And the orbit of the star tell us about the thing that's making the star orbit. In 1988, David Latham at Harvard and his team of collaborators published this measurement in which they asserted that they had discovered with this technique an object with the mass of at least 11 Jupiter masses. The object could not be smaller than that, but it could be bigger than that, in orbit around the star HD 114762. So this object gets the fancy name HD 114762b. So what are we looking at? The vertical axis is known as radial velocity. Radial velocity means toward or away. All they're measuring is the blue shift or red shift, toward or away. They're not measuring sideways motion, just toward or away, toward or away. The radial velocity and the horizontal axis is phase, which just means time. And you see each point or x is a data point, and the velocity of the star is going down and up and down and up and down and up. There's a lot of scatter in the diagram. But it's pretty clear. The velocity of the star is going down and up and down and up. And if you pick any one point, let me pick right here. You say, okay, we made a measurement right there, and the star's velocity is at 49 kilometers per second. Is it, on that day, is it 49 kilometers per second? Yeah. Maybe it's 49.2 or 49.3 or 48.87. There's some noise. But it's quite clear that sometime later, you make a measurement up here, it's at 50 or 50.1 or 49.8. It's changing. And it's changing in a pretty dependable way. And they had 10 years of data. And in that 10 years, they found that this object goes back and forth like this with a period of 84 days. With a total amplitude, blue shifted, red shifted, blue shifted, red shifted, of 1.2 kilometers per second. So it goes maximum red shifted 0.6 kilometers per second, maximum blue shifted, I'm going the wrong way, maximum blue shifted 0.6 kilometers per second, maximum red shifted 0.6 kilometers per second, for a total amplitude of 1.2 kilometers per second from bottom to top of that curve. Now you'll notice this plot says 48, 49, 50, 51 kilometers per second. Now I want to emphasize what's in the brackets there, the units, kilometers per second. That's what astronomers could measure, kilometers per second. And they could measure this at about a few tenths of kilometers per second. This was astounding that they could do this. And when they published this, they weren't sure what they had. This might be a brown dwarf. It wasn't a star. There's no way it was a star. It might be a brown dwarf. Might be a planet. What's a brown dwarf? A brown dwarf is something smaller than a star, but bigger than a planet. A brown dwarf is an object that's capable of doing something a star can do, which is nuclear fusion, to generate energy. But a brown dwarf can only do nuclear fusion with a kind of material called deuterium, which is heavy hydrogen. And a brown dwarf and stars don't have much deuterium. So they run out of it after a few million years, and then they're out of fuel. And then they just cool off and die. But planets can't do that, so planets never get to do any nuclear fusion. Yes?
I understand the part you just said about the nuclear fusion. But it began by defining that as something smaller than the sun bigger than the planet. Is there, by definition, a maximum mass of the planet? And why could a planet not be that big?
It takes a certain amount of mass for gravity to be strong enough to squeeze the planet hard enough to make the pressures and temperatures at the center great enough for that nuclear fusion process to turn on. Depending on which astrophysicist you talk to, and depending on exactly what the planet might be made of, that boundary between planet and brown dwarf might be 11 times the mass of Jupiter, or 12, or 13, or 14. It's right in there. It's not 8. If you're 8 Jupiter masses, you're a planet. If you're 10 Jupiter masses, you're a planet. If you're 20 Jupiter masses, you're a brown dwarf. If you're in that 13, 14 region, it depends on which theorist you're talking to that day. All right? If you're 40 Jupiter masses, you're a brown dwarf. If you're 5 Jupiter masses, you're a planet. So this guy is in that nether region. And again, for this radial velocity technique, since you're only measuring the velocity toward and away, you don't get all the information about the planet or about the star, because we don't know whether the orbit of the planet is coming completely toward you and away from you, or whether the planet's orbit is tilted up and down and up and down, or even is going up like this and down like this. And if the orbit is way up like this and down like this, then the component of the planet's motion toward you and away from you is just a tiny little bit of the planet's motion. Most of the motion's up like this, and it could be a whopping big object, and you're only measuring a little bit of its motion. So this could be 50 Jupiter masses, but it probably isn't. But it could be. Okay? So that's why they hedged their bets and then said it's a probable brown dwarf, but it could be a really big planet. Yes?
Is the solid line just a mean or an average of all those readings?
Yeah, the solid line is their best fit to the data.
At one time was always larger, wasn't it? It was a sun or a star that collapsed.
A brown dwarf? Planets and brown dwarfs always both had to form out of something once upon a time. So they were always both bigger from bigger stuff at one point, but the process of forming planets and brown dwarfs could have been different. But the process that formed a giant planet like this could have been the same process that formed a brown dwarf. Could have been. We weren't there to watch, so we don't know. All right. So how fast do planets make stars move? The speed increases linearly with the mass of the planet. You got to know that. Okay? And the speed decreases with the square root of the distance from the planet. You knew that. Okay? So what does that actually mean in terms of numbers? How fast does the Earth make the sun move? Well, we know the Earth's mass, we know the sun's mass, we know the Earth's distance from the sun. The Earth makes the sun move 10 centimeters per second. Not much. How fast does Jupiter make the sun move? 12 meters per second. If you replace the Earth with Jupiter, Jupiter's 318 times the mass of the Earth. How fast would Jupiter make the sun move if the Jupiter were where the Earth is? 32 meters per second. If Jupiter were 10 times closer to the sun than the Earth is, how fast would Jupiter make the sun move? 100 meters per second. Could we measure that? Well, yes. So this is data from 1995. This is the breakthrough plot. The first discovery of a Jupiter-type planet around a sun-like star. This is the radial velocity technique, the star's motion away from and toward the Earth. And look at the numbers on this plot, minus 50, plus 50, and look at what is in that plot. It's not kilometers per second. That's meters per second. Meters per second. There was a breakthrough in the early 1990s in which astronomers finally figured out how to measure these velocities in meters per second. And there are now folks, 20 years later, who can measure the motions of stars at about 1 meter per second. 1 meter per second, the motions of stars. Which means we can use this technique to detect fairly small planets. This technique has been used to discover lots of planets. One more technique, the transit method, and then we're done for the day. The transit method is used to detect the presence of planets by measuring the brightnesses of stars. When the planets pass in front of the stars, they eclipse the stars, like this. So here's the moon passing in front of the sun. When it does that, the sun gets a little bit fainter, right? So if a planet does that, the star gets a little bit fainter. So the moon passes in front of the sun, and for some small amount of time, the sun gets a little bit fainter. So you measure the brightness of the star and watch it get fainter and then brighter again. This was a transit of Venus in 2012. Here's Venus passing in front of the sun. And it took about 6 hours for Venus to go all the way across the surface of the sun, to go from one end of the sun across the other. And while it was in front of the sun, it blocked out about 0.1% the light of the sun. So if you measure the brightness of the sun as a function of time, and it gets fainter by a little bit and then brighter, you could detect the presence of Venus. Now, Venus goes in front of the sun twice every 200 years. So that's a tough way to discover that Venus exists. But there are other planets who do this a little bit more regularly. So if you have a planet orbiting a star, here's the planet, it passes in front of the star just like Venus did. You measure the brightness of the star, and the brightness goes down, and then the brightness comes back up, what astronomers call a light curve. You can detect the presence of the planet. And if the planet does that regularly, a little bit more regularly than Venus does that as seen from the Earth, you can detect the presence of a planet. So here is that kind of light curve. We're at 100%, 1 right here, each data point with an error bar, and the light from the star is pretty steady, and then boom, the bottom drops out. Why does it drop out? Because a planet passed in front of the star, and it dropped by not very much. We're now down by 1% right here. And these error bars are about 0.1%. These are really tiny error bars. We can do this from the ground, and we can do this from space. From the ground, it's a little harder to do. From space, it's a little easier to do. But there are probably 100 different groups of astronomers around the world using this technique to detect planets. And lots of planets have been detected with this technique. If there are multiple planets in a system, you would get multiple eclipses. Now, if the star-planet system is not oriented right, you won't get any eclipses. And you won't detect them. You'll only detect eclipses if the planet system is oriented such that the planets pass in between the star and us. So only a small fraction of the stars will have planets that are detectable through the transit technique. But some of them will. And if we have those systems, we can detect multiple planets. And a lot of planets have been detected that way. This illustrates, here we have the 100%, we have a drop down to 99.5% of the light. The time between eclipses tells us the orbital period. Here it's 4.887 days. That's the orbital period of the planet. This is a blow up here of one of the eclipses and the shape of that eclipse. And the duration of the eclipse, 0.217 days or 5.28 hours. That actually enables us to measure the size of the planet. With the transit technique, we can measure how big the planet is. So we know from this technique, is it a planet the size of the Earth? Is it the planet the size of Jupiter? A planet the size of Saturn? So with the transit technique, we can start talking about Jupiter-sized planets, Saturn-sized planets, Earth-sized planets, Mercury-sized planets. We can learn more about the planets this way. The Kepler satellite, which was a NASA mission launched in 2008, was designed specifically with the purpose of detecting planets around other stars using the transit technique. And Kepler observed about 150,000 stars. and has already detected more than 1,000 planets around other stars. It has several other planet candidates that it has detected. They're identified only as planet candidates because once Kepler detects them, the requirement is that those objects have follow-up observations from ground-based telescopes in order to confirm that they truly are planets. But Kepler has several thousand other candidate planets that it has detected. Vanderbilt's involved in this game. Vanderbilt has our very own telescope. It's called KELT, the Kilodegree Extremely Little Telescope. KELT is sited in South Africa. There's also a KELT North telescope, which is in Arizona. And KELT uses the transit technique to detect planets. KELT South has not yet detected any planets, but KELT North has detected a small handful of planets. NASA is planning another mission known as the TESS mission. TESS will probably be launched in 2018. I think it's scheduled for a 2017 launch, but I don't think they'll make it. Okay. But TESS is designed to detect planets using the transit technique around planets in the solar neighborhood. It will presumably detect thousands of planets. I suspect it will detect tens of thousands of planets in the solar neighborhood using this technique. Between Gaia and TESS and all the ground-based techniques, the radial velocity technique, the transit technique, the astrometry technique, we will have catalogs in the next decade with probably hundreds of thousands of planets known around other stars. So where are we? Next week, my plan is to actually talk about a handful of the most interesting planets that we know about around other stars, to introduce you to these planets. And then in the last 3 weeks, we'll move on, having convinced you that we actually know how to detect planets and that we know about these planets. We'll then talk about the implications of those planets.